You usually expect geometry to be something anchored in physical reality. Like when you sketch a parabola on a piece of paper, you see the curve.
Right, exactly. It's visual.
Yeah, and when you look at the steel cables of a suspension bridge, the mathematics is right there. It's holding up the concrete. It's tangible. But if you take a step into modern algebraic geometry, that physical intuition just completely evaporates. The paper disappears.
It really does. You find yourself analyzing this geometric landscape that is, well, completely invisible to the naked eye. It's governed entirely by the abstract algebraic properties of polynomial equations.
Which is wild to think about.
It represents one of the most profound paradigm shifts in mathematical history, honestly. The discipline moved away from drawing shapes in a coordinate space. Instead, it turned its focus inward, studying the structural DNA of the equations that generate those shapes.
Right.
So mathematicians began operating in dimensions and abstract spaces that the human brain simply cannot visualize.
Okay, let's unpack this. Because today, you and I are going to tear through an incredible stack of material that documents exactly how this subject operates, and honestly, how human beings actually manage to learn it.
Which is a feat in itself.
Oh, absolutely. We are looking at the course syllabi and detailed class notes from ETH Zurich. Specifically, the course is taught by Johannes Schmidt and Andreas Gathman.
Those are fantastic resources.
They really are. And we also have excerpts from Ravi Vakil's famous ever-evolving textbook, The Rising Sea, plus analysis of the pedagogical frameworks and the community-driven shadow ecosystems,
Yeah, the blog interactions, the DMath forum posts.
Exactly, the places where students are essentially surviving this subject together. So our mission today is to demystify algebraic geometry.
I love it.
We're going to figure out how mathematicians visualize the invisible, how they translate the rigid rules of algebra into these sweeping topological shapes, and how this seemingly esoteric machinery provides the exact vocabulary physicists use to describe the quantum fabric of string theory.
It's a huge journey, but the historical evolution is crucial here. If you want to understand the abstraction, you first have to understand the concrete problem it was actually built to solve.
Right, you need the foundation first.
Exactly. The classical foundation of algebraic geometry is the study of varieties. In the simplest terms, an affine variety is the geometric space defined by the vanishing of a set of polynomial equations.
And by vanishing, we just mean finding the roots, right?
Yeah.
Setting the polynomial to 0 and mapping out the solutions, just like finding where a basic quadratic equation hits the x-axis.
Yes, exactly. But let's escalate this immediately to the foundational classification outlined in the ETH sources. Consider an affine variety in a one-dimensional complex space, C.
Okay, keeping it in one dimension for now.
Right. But you aren't just dealing with one simple equation. You might have a massive system of single variable polynomials, like f1 of z, f2 of z, all the way to fr of z.
Oh, wow, so a whole bunch of them.
Yeah, and you are looking for the shared zero set, the specific points in the complex plane where every single one of those equations vanishes simultaneously.
So you have this chaotic system of competing equations all trying to carve out a shared territory.
Precisely. But because we are working over the complex numbers in a single variable, the algebra imposes a massive restriction on the geometry. The ring of polynomials in one variable over a field is a principal ideal domain.
A principal ideal domain. Okay, how does that work in practice?
It basically acts as a mathematical funnel. The principal ideal domain guarantees that any ideal generated by that chaotic list of polynomials can actually be generated by a single polynomial.
Wait, really? Just one?
Just one. Their greatest common divisor, let's call it g of z. The shared zero set of the entire system is perfectly identical to the zero set of just g of z.
That's crazy.
Yeah, the algebra collapses the complexity instantly.
Which means we only have two geometric outcomes for our variety, right? If g of z turns out to be the zero polynomial, every point in the complex space is a solution.
Right. Your variety is the entire affine line.
But if g of z is anything else, anything at all, the fundamental theorem of algebra dictates that it factors into a finite product of linear terms.
Exactly. So geometrically, your variety is just a finite set of distinct, disconnected points.
That is the bedrock classification in one dimension. You don't get line segments. You don't get open intervals. You either get the whole space or you get a handful of dots.
The algebra dictates a highly rigid geometry there. But, as you move into higher dimensions, the zero sets of polynomials become intricate geometric objects. curves and surfaces.
And these objects can possess imperfections, right? They can have sharp corners or self-intersections.
Yes, and the classical framework provides a way to detect these topological imperfections using purely algebraic tools. We see this explicitly in the gradient criterion for singularities.
Okay, this is where we assume you, listening at home, are somewhat comfortable with multivariable calculus. If you have a curve in a plane, classical geometry says it's smooth if you can define a unique tangent line at every point.
Right, but an algebraic equation doesn't have eyes. It can't look at a graph.
Right, so it detects a singularity, like a node, a cusp, a sharp corner, by analyzing its own partial derivatives. The Jacobian matrix essentially maps the tangent space.
Let's apply it, and just to make it concrete. Consider the unit circle, defined by f of x, y equals x squared, plus y squared minus 1 equals 0.
Okay, standard unit circle.
To analyze the tangent space dimension, you find the gradient vector by taking the partial derivatives with respect to x and y, which gives you the vector 2x, 2y.
Okay, and the gradient criterion dictates that a singularity exists only at a point on the variety where this entire gradient vector vanishes, where it hits 0.
Exactly. And the only coordinate where 2x, 2y is equals 0, 0 is the origin. 0, 0.
But if you plug the origin back into the defining equation, 0 squared plus 0 squared minus 1, you get -1, not 0.
Right. The point where the gradient vanishes does not actually live on the variety. Therefore, the algebra rigorously proves that the unit circle possesses no singular points.
It is flawlessly smooth. That makes total sense.
Now contrast that with the nodal cubic curve. The equation is y squared minus x cubed minus x squared equals 0.
Okay, a bit more complicated.
The gradient vector here is -3x squared minus 2x, comma 2y. If you set this to 0, you find the gradient vanishes at -2/3, 0, and at the origin, 0, 0.
Okay, and if you test those coordinates against the original equation, -2/3, 0 fails. It doesn't equal 0.
Right.
But the origin 0, 0 satisfies the equation perfectly. 0 minus 0 minus 0 is 0. So the gradient vanishes at a point that actually lives on the curve.
Exactly. The algebra has flagged a structural breakdown. Geometrically, if you trace this cubic curve, it passes through the origin, loops out into the plane, and crosses directly back over itself through the origin again.
Oh, wow.
Yeah, and at that exact self-intersection, the curve possesses two distinct tangent directions simultaneously. The local dimension of the tangent space has artificially jumped, mathematically proving the existence of a singularity.
It's such an elegant translation device. I mean, you don't need to graph the cubic curve to know it crosses itself. The local ring structure of the polynomial tells you everything.
It really does.
And this brings us to one of the most aggressive claims in the classical theory, something the sources highlight as a massive stumbling block for intuition: Krull's principal ideal theorem.
Yes, Krull's theorem is the absolute backbone of dimension theory in commutative algebra. It formally states that in a Noetherian ring, the height of a minimal prime ideal over a principal ideal is at most 1.
Okay, which, translated out of the algebraic jargon and into the geometry, means that every time you impose one new non-redundant polynomial equation on a variety, the geometric dimension of that variety drops by exactly 1.
That's a great way to put it.
Think of it like a sculptor with a block of marble, right? The 3D space is the marble. One strike with the chisel, which is our equation, slices away exactly one dimension, leaving a 2D surface. A second equation carves out a 1D curve.
It mathematically guarantees that the chiseling restricts the space in a uniformly predictable way.
Wait, hold on, though. This is where classical intuition falls apart for me.
How so?
Well, if I have a massive chaotic polynomial equation with 50 variables and a degree of 10,000, it is a monstrously complex mathematical object.
It is.
If I impose that single equation onto a 15-dimensional space, you're telling me it just neatly shaves off a single dimension, it doesn't shatter the space, it doesn't collapse multiple dimensions if the equation folds back on itself in some pathological way.
Nope.
How can Krull's theorem guarantee such a uniform drop across the board?
Because the theorem relies on the intrinsic properties of prime ideals in Noetherian rings, which inherently forbid infinite descending chains of algebraic restrictions.
Okay.
Even a polynomial with a degree of 10,000 in 50 variables acts as a single hypersurface. No matter how wildly that hypersurface folds, twists, or self-intersects within the 15-dimensional ambient space, its core geometric dimension remains 14.
Because it's still just one restriction on the degrees of freedom.
Exactly that. And this is why mathematicians rely so heavily on the Algebra Geometry Dictionary.
Right. When an algebraic geometer is operating in a 15-dimensional space, visual intuition is entirely dead. The brain simply cannot process a 14-dimensional hypersurface.
Obviously not.
But because Kroll's theorem is rigorously proven within the algebra, the mathematician can trust the algebraic calculation implicitly. The ring of polynomials provides the structural integrity that the human imagination lacks.
Okay, so the classical framework works beautifully over the complex numbers. You have a rigid structure, you can hunt down singularities, you can track dimensions. But the sources reveal a massive paradigm shift in the mid-20th century. The classical coordinate-based approach hit a wall, right? Particularly when mathematicians wanted to apply these geometric tools to other fields like number theory.
Yes, this was the dawn of the Grothendieck revolution. Alexander Grothendieck and Jean-Pierre Serre dismantled the classical scaffolding and rebuilt algebraic geometry from the ground up.
It was a total overhaul.
David Mumford, who's a Fields medalist, famously joked that algebraic geometry adherents were secretly plotting to take over all the rest of mathematics. They weren't really joking, though, were they?
Not at all. The machinery Grothendieck built was so generalized that it fundamentally rewrote topology, complex analysis, and arithmetic geometry.
And our guide for understanding this shift is Ravi Vakil's continuously updated text, The Rising Sea. The title itself is a statement on how modern mathematics should be done, right? It's a metaphor Grothendieck himself used.
Yes. The metaphor contrasts two approaches to solving a difficult mathematical problem. The traditional approach is like trying to crack a nut with a hammer.
Okay.
You use intense, focused, specialized techniques to hit the problem head-on. Sometimes you crack the nut, but often you just smash it to unrecognizable pieces.
But the Grothendieck approach is the rising sea. You don't strike the nut.
Right.
You introduce a vast, broad, incredibly general theoretical framework.
Right.
You let the water level of the theory slowly rise around the problem. You build up the categorical structure, the sheaves, the schemes, until the general theory is so high that the specific problem just effortlessly floats away.
Exactly. The solution becomes a trivial consequence of the environment you've constructed. It demands structural understanding over clever computational tricks.
Which is so elegant.
To build this rising sea, to transition from classical affine varieties to modern schemes, Grothendieck required three simultaneous, massive generalizations of the geometry.
Okay, let's figure out these leaps. If we are generalizing away from classical geometry, well, classical math demands exact, perfect solutions. But if we look at adjacent fields like analysis, mathematicians care deeply about approximations and infinitesimals. So Grothendieck had to allow those infinitesimals into the algebra, which means allowing elements that square to zero.
Nilpotence.
That is the first monumental leap. In a classical coordinate ring, if you have a function and its square is zero everywhere on the space, the function itself must be zero everywhere. The classical ring is a reduced ring.
Okay.
But in scheme theory, we explicitly allow nilpotent elements. We allow functions that are not zero, but some power of them is zero. It fundamentally changes what a point is, doesn't it? The geometry remembers not just the location of the point, but an infinitesimal neighborhood around it. The space becomes fuzzy.
Fuzzy is a good word for it. The second leap addresses the limitations of global coordinates. If you study differential geometry, you know that you don't use a single global coordinate system to map a sphere.
Right, you use an atlas of overlapping local patches, and you define transition functions to glue them together.
Exactly. So algebraic geometry adopted that local to global gluing. Instead of forcing a variety to live entirely inside one massive affine or projective space, you build an abstract shape by gluing together local affine schemes.
This freed the geometry from the rigid embedding space. An affine scheme becomes the local page in the atlas, and the global scheme is the manifold assembled from those pages.
Which brings us to the third leap, which seems entirely driven by number theory.
Right.
Classically, we're working over the complex numbers because the field is algebraically closed. Every polynomial has roots.
But number theorists don't care about the complex plane. They want to know if an equation like Fermat's last theorem has solutions using only integers.
Grothendieck accommodated this by demanding that geometry must be able to operate over arbitrary commutative rings. You no longer need an algebraically closed field.
Oh, wow.
You can build a geometric space, a scheme, over the ring of integers. By doing this, Grothendieck allowed mathematicians to wield geometric concepts like intersection theory, tangent spaces, and cohomology, and apply them directly to purely arithmetic equations.
But wait, if we've completely abandoned coordinate space for these arbitrary rings, and we're gluing fuzzy nilpotent patches together, how do we even know what we're looking at anymore?
It's tough.
The abstraction is so dense it feels completely untethered from reality. You aren't drawing circles anymore, you're just manipulating functors and categories.
This is exactly what Ravi Vakil warns students about in The Rising Sea. It is incredibly easy to become seduced by the categorical machinery and lose sight of the geometry. He explicitly warns against becoming one of the lotus eaters of infatuation with untethered abstraction.
Like the sailors in the Odyssey. Just getting high on category theory and forgetting to actually sail home and solve a concrete math problem.
Exactly. The category theory, defining mathematical objects not by what they are internally made of, but strictly by how they relate to other objects via morphisms, that is a tool. It is the rising sea.
Right, it's a means to an end.
But the end goal is still to answer naive, fundamental geometric questions. How many lines lie on this cubic surface? What is the structure of this moduli space? The abstraction is only justified because it is the absolute only way to answer those questions rigorously.
Which means we need to figure out how to visualize the unvisualizable. We have to map out what these schemes actually look like in the mind's eye.
Yes.
The text quotes the mathematician Sophie Germain. She said, "Algebra is but written geometry. Geometry is but drawn algebra." So how do you draw a scheme?
Well, you have to dramatically expand your definition of a point. Let's look at the prime spectrum of a ring. In classical geometry, points correspond to maximal ideals. But in a scheme, every single prime ideal becomes a point in the geometric space.
This introduces the concept of the generic point. If we look at the affine line over the complex numbers, we have our standard points for every complex number. But because we include all prime ideals, we also include the prime ideal generated by 0, denoted as bracket 0.
The generic point is notoriously difficult for students to conceptualize. It exists within the topological space of the scheme, but its closure is the entire affine line.
The sources describe it in this almost philosophical way. It is a point that is somewhere on the line, but nowhere in particular.
Okay.
It isn't at coordinate 1 or pi or 0. It is intrinsically near every classical point simultaneously, but it cannot be pinned down to a specific location. It acts as the mathematical avatar for the entire line.
And that omnipresence is mathematically vital. Because the generic point is dense in the space. If you can prove that a certain algebraic property holds at the generic point, it immediately implies that the property holds for a dense, open subset of the entire scheme.
Oh, that's clever.
You don't have to check an infinite number of individual classical points. You just interrogate the generic point.
It's an incredible shortcut.
Yeah.
But the generic point isn't even the weirdest part of a scheme.
Yeah.
We have to address the fuzz, the nilpotent elements we discussed earlier.
Yes. The fuzz.
The sources go into heavy detail about visualizing non-radical ideals. Let's take the polynomial ring, C adjoint x modulo, the ideal generated by x squared.
Okay.
Classically, if you set x squared equals 0, the only solution is 0. The variety is just the origin. But as a scheme, spec C adjoint x modulo x squared contains more information.
It acts as the origin plus an infinitesimal halo of fuzz. The mechanism here relies on how polynomials map into this quotient ring. Because the ideal is generated by x squared, any polynomial mapped into this space is essentially truncated after the linear term.
It's keeping the Taylor expansion of the polynomial, but aggressively cutting off anything degree 2 or higher.
Exactly. So it retains the constant term, which is the value of the polynomial at 0, and it retains the coefficient of the linear term, which is the first derivative at 0.
And if you look at C adjoint x modulo x cubed, the point gains a thicker layer of fuzz. The quotient ring retains the value, the first derivative, and the second derivative.
Right. It stores even more local data.
You know, this clicked for me when I thought about photography.
Oh, really?
Yeah. If a classical reduced point in geometry is a still photograph, just a frozen coordinate in space with no temporal data, then a nilpotent scheme-theoretic point is like a live photo on your smartphone.
Okay, I like that.
Yeah.
How does the live photo capture the nilpotent structure?
Well, when you take a live photo, the file doesn't just save the exact spatial arrangement of the pixels at millisecond 0, right? It captures a fraction of a second of video before and after. It encodes motion. A classical point just says, the curve is located at coordinate 0. But the nilpotent point, C adjoint x modulo x squared, is the live photo.
Right.
It captures the exact location, the value at 0, but it simultaneously encodes the momentary velocity, the first derivative.
That's a great analogy.
And if the ideal is x cubed, it captures the location, the velocity, and the acceleration. It's a single point that possesses dynamic, directional data about how a curve is passing through it.
That analogy maps perfectly onto intersection theory, which is really the primary reason growth index necessitated nilpotence.
Right.
In classical geometry, if a parabola slowly moves toward a flat line until it becomes perfectly tangent, they intersect at exactly one point. The classical geometry just registers a single point of contact. It entirely loses the history of the collision.
It just registers a binary,
But
a touch.
But scheme theory registers the multiplicity of the intersection. When that parabola becomes tangent to the line, the intersection scheme isn't just a reduced point, it becomes C adjoin x modulo x squared. It becomes a fat point.
The algebra inherently remembers that this single point of contact is actually the result of 2 points colliding and merging.
Yes. The nilpotent fuzz preserves the conservation of intersection numbers. It provides a high-definition resolution of the geometry that classical varieties are just blind to.
It tracks the collision, gives us high-definition geometry, but it creates a massive logistical nightmare.
It sure does.
If my local affine patch is tracking all this microscopic nilpotent fuzz, and your overlapping affine patch is doing the same, how do we synchronize? How do we ensure we're looking at the same global shape when we glue these patches together over arbitrary rings?
You're pointing directly at the necessity of the affine communication lemma. This is the operational workhorse of scheme theory. It provides the strict mathematical protocols for checking properties affine locally.
So if I want to prove a global scheme is Noetherian or smooth, I don't have to look at the entire massive structure at once.
No, you interrogate your local affine patch. The lemma relies on distinguished open sets. These are smaller, localized algebraic rings formed by inverting a single element.
Okay. It proves that if a property holds on your specific affine chart and another mathematician computes the same property on their overlapping chart, there's a guaranteed algebraic translation via these distinguished open sets.
Oh, I see.
The local algebraic data is guaranteed to stitch together without contradiction, ensuring the global geometry is structurally sound.
It's the synchronization protocol for the rising sea. But as we transition from the mathematical mechanics to the reality of the classroom, a massive question arises. How do you wire a human brain for this?
It is not easy, let me tell you.
I mean, how do you teach a graduate student whose brain evolved to throw spears in three-dimensional space to intuitively manipulate nilpotent live photos and generic points?
Yeah, teaching algebraic geometry is notoriously brutal. The cognitive load required just to understand the definitions is immense.
The sources provide a deep comparative analysis of the pedagogical ecosystem, heavily featuring the syllabi from ETH Zurich, right?
Yes, and Johannes Schmidt's 2024 and 2026 courses at ETH Zurich illustrate a very modern, aggressive intervention to mitigate this learning curve. The flipped classroom.
Right. Instead of the traditional model where a professor stands at a chalkboard for 2 hours, writes out endless proofs, and hopes the students can copy them down while simultaneously comprehending them, Schmidt inverts the entire dynamic.
Which is brilliant.
The students consume the raw information outside of class. They watch 10 to 20-minute, highly condensed YouTube videos of whiteboard notes.
The digital format is crucial here. A student can pause, rewind, or slow down the explanation of a complex categorical limit. They control the pace of their own cognitive intake.
And this frees up the actual classroom time. When they gather on Mondays or Tuesdays, it's not for a lecture, it's a live problem-solving arena. The students form groups and wrestle with the algebraic machinery in real time.
While the lecturer and coordinators like Tim Geringer and Dmitry Krakow circulate the room, unblocking them when they hit a wall,
this active communal struggle is necessary because the textbooks in this field are uniquely demanding. The sources contrast 3 major pillars of the literature. First, you have Andreas Gathman's notes.
Gathman serves as a bridge. He is highly structured, beginning firmly in the classical realm of affine and projective varieties, before gently introducing sheaves and cohomology much later.
He attempts to build the intuition before deploying the abstraction.
Exactly.
Then you have Ravi Vakil's The Rising Sea. Vakil's approach is radically different. He adopts a highly conversational tone, speaking directly to the reader, but he drops you straight into category theory from page 1.
It's an immersion technique.
But the defining feature of The Rising Sea is that it's a living document. The sources mention students like Wanmin Liu creating searchable HTML versions and a constant stream of blog interactions where readers submit typo fixes.
It's amazing. The community is literally actively compiling the textbook as they learn the subject. It acts as an open-source mathematical project.
But then, looming over the entire discipline, is Robin Hartshorn's algebraic geometry. Published in 1977, it remains the undisputed, terrifying standard of the field.
Oh, hartshorn.
Everything I read in the sources suggests that hartshorn is a trial by fire. It expects an incredibly deep fluency in advanced commutative algebra right out of the gate. But the true infamy of the book lies in its exercises, right?
Hartshorn is legendary because major foundational theorems of the discipline are entirely absent from the main text. They are relegated to the exercises.
Wait, really?
Yes. Hartshorn simply provides a brief setup and commands the reader prove this.
That is ruthless. The sources highlight specific nightmares students face, like mastering elimination theory or calculating strict transforms under blowups. Let's look at that. If I have that nodal cubic curve with the self-intersection at the origin and I want to blow up the origin to resolve the singularity, what am I actually doing? Why is it so hard to calculate?
Glowing up is a surgical procedure in algebraic geometry. You are taking the origin, a single point, and replacing it with an entire projective line called the exceptional divisor.
Okay.
You are essentially separating out every single tangent direction that passes through the origin.
So when the cubic curve crosses itself at the origin, it has two different tangent lines. By blowing up the point into a whole line of tangent directions, the two strands of the curve get pulled apart.
Exactly. They now intersect the exceptional divisor at two distinct separate locations. The singularity is resolved. The curve is now smooth.
Geometrically, it is beautiful.
Oh.
But algebraically, it sounds like a labyrinth.
Oh, it is. To calculate the strict transform in hartshorn, a student has to define the blowup using a graded ring of an ideal. Then pull the equation of the cubic curve into this new, higher dimensional space.
That was messy.
Very. You have to carefully factor out the equation of the exceptional divisor and then calculate the result across multiple overlapping affine charts just to see the new smooth curve.
It's a massive error-prone calculation, which leads me to a fundamental question about the pedagogy here.
What's that?
If algebraic geometry is this unified foundational canon, why is there such a massive philosophical gap between hartshorn's uncompromising sink-or-swim rigor and Vakil's conversational, community-driven handholding? It feels like trying to learn to swim by either reading a dense physics textbook on fluid dynamics or just being thrown directly into the middle of the ocean during a hurricane.
That's a fair comparison. The divergence in pedagogy is a direct reflection of the subject's vastness. There is no single cognitive path that works for every mind. The sheer steepness of the learning curve requires disparate on-ramps.
Right.
Hartshorn's methodology is designed to forge absolute self-reliance. By forcing the student to build the foundational theorems from scratch, they develop the raw mathematical muscle required to survive in uncharted research territory.
And Vakil.
Vakil, conversely, recognizes that the cognitive load of growth NDX machinery is so high that providing conversational guardrails prevents a massive attrition rate.
And because of this extreme difficulty, the sources highlight a shadow ecosystem of survival. Graduate students cannot solve Hartshorn's exercises in isolation. They have to form study groups. They rely heavily on community-compiled solution guides, Stack Exchange threads, and the DMath forum at ETH.
It's a collective effort.
The stereotype of the isolated, lone genius mathematician completely breaks down here. Algebraic geometry is an inherently social endeavor because the machinery is just too heavy for one person to lift alone.
They band together to survive the abstraction. But, the ultimate question is, to what end? Why subject yourself to the gradient criteria, the nilpotent-fuzz, the affine communication protocols, and the brutal blow-up calculations?
Right. What is the payoff? This brings us to the final and honestly most mind-bending section of our deep dive, the multidisciplinary payoff.
This is where it gets really fun.
The rewards for mastering this abstract architecture exist both purely within the realm of mathematics and deep within the physical fabric of the universe. Let's start with the pure math. The sources, both Gathman Chapter 11 and Vakil Chapter 27, dedicate significant space to a classic result. The 27 lines on a smooth cubic surface.
And it's one of the most stunning, almost magical numerical constants in geometry. A smooth cubic surface in projective space is defined by a degree 3 polynomial in 4 variables.
Okay, and visually?
Visually, it is a smooth, curving, bulbous, entirely non-linear topology. Yet, embedded perfectly within the contours of this curved surface are exactly 27 perfectly straight lines.
Exactly 27.
Not 26, not 28. Exactly 27, regardless of how you deform the smooth cubic.
That sounds impossible. How can an intrinsically curved shape hide exactly 27 straight lines? And how does algebraic geometry actually find them? We aren't just guessing and checking equations, right?
No, it requires advanced intersection theory and parameter spaces. Mathematicians approach this by viewing the cubic surface not just as a random shape, but as a blow-up of the projective plane at 6 general points.
Okay, we just talked about blowups. So you take a flat plane, you pick 6 points, and you blow them up into 6 exceptional divisors.
Yeah.
6 lines.
Right.
So there's 6 lines right there.
Precisely. Then, in the original plane, you can draw exactly one line through any pair of those 6 points. Combinatorics tells us there are 15 such pairs.
Okay, 15 lines connecting the points.
When you pull those 15 lines up into the blown-up surface, they become 15 more straight lines on the cubic.
So we have 6 from the blowups plus 15 connecting the points. That's 21 lines. Where are the last 6?
The final 6 come from the conics. In the projective plane, you can draw exactly one smooth conic curve passing through any 5 of those 6 points. There are 6 ways to choose a set of 5 points.
I see where this is going.
When you pull those 6 curved conics up into the blow-up, the geometry forces them to straighten out into 6 lines. So 6 plus 15 plus 6 equals 27 lines.
The geometry completely orchestrates the combinatorics. And the algebraic machinery, the blowups, the divisors, the intersection theory is the exact tool set required to prove that these are the only lines and that they must exist on every smooth cubic surface.
It's an incredible aesthetic triumph.
It really is. But the payoff of algebraic geometry isn't just discovering beautiful numerical coincidences. It literally dictates the cutting edge of quantum physics.
This is where the true power of the Grothendieck revolution is fully realized. The sources dive into the research of Wonmin Liu, illuminating how algebraic geometry provides the fundamental architecture for string theory and mathematical physics.
Okay, so string theory is attempting to model the most fundamental microscopic nature of particles, gravity, and quantum forces. To do this, physicists require a mathematical framework capable of handling incredibly complex higher dimensional symmetries. And they found that exact framework sitting in the most abstract, untethered corners of algebraic geometry. Triangulated categories.
To understand how physicists use this, we have to look at the derived category of coherent sheaves. In a classical abelian category, like the category of modules or vector spaces, you are looking at exact sequences.
Wonmin Liu uses a brilliant analogy for this. Imagine the classical abelian category as existing entirely on the ground floor of a building. It's flat. The objects just sit on the floor.
But when you construct a derived category, you replace those single objects with entire chain complexes. An object in the derived category is a sequence of objects and morphisms spanning across multiple degrees.
The triangulated category is a giant skyscraper with infinitely many floors, striking up into positive infinity and down into negative infinity.
Right.
The objects in this category, the chain complexes, don't just live on the ground floor. They are massive structural entities that span across multiple floors simultaneously. And the morphisms, the mathematical relationships between these objects, can shift up and down the elevator shafts of the skyscraper.
This mathematical architecture maps flawlessly onto the physics of string theory. In string theory, the physical objects known as D-branes, which are the multidimensional membranes that strings attach to, are modeled mathematically as these exact giant objects.
Yeah.
These complexes spanning the floors of the triangulated category.
So the algebraic geometry built an infinite abstract skyscraper of complexes, and physicists realized that D-branes are the exact entities living inside that architecture.
Yep.
And the open strings, the fundamental vibrational strings connecting the D-branes.
The open strings correspond precisely to the morphisms, the derived relations, shifting between the objects in the category. The algebraic geometry isn't just describing the physics, it is providing the literal syntax and vocabulary required to articulate quantum gravity.
Which brings us to a massive breakthrough introduced by Tom Bridgeland in 2002. Bridgeland's stability conditions.
If we have this infinite skyscraper filled with D-branes, we need a way to organize them and determine which ones are physically viable, right? Exactly. Bridgeland combined two concepts. A central charge, which maps the abstract categorical objects to complex numbers, assigning them a mass and a phase, and a slicing, which is a rigorous way to partition the floors of the triangulated category.
And when you map out every possible stability condition for a given category, it doesn't just form a list. It forms a complex manifold, a topological space composed entirely of stability conditions.
Yes. The stability of the category generates its own geometry. And within this stability manifold, physicists and mathematicians study wall crossing. The manifold is divided into chambers by walls of marginal stability.
What happens when a D-brane moves through the manifold and crosses one of those walls?
Physically, it represents a phase transition or the decay of a fundamental particle. The D-brane goes from being stable to unstable, breaking apart into smaller components. The wall-crossing formulas in algebraic geometry perfectly calculate the exact invariant changes during these physical phase transitions. Concepts that seemed like the ultimate untethered abstraction, nilpotent fuzz, derived categories, generic points, end up being the ultra-precise surgical tools required to solve homological mirror symmetry.
It is absolutely breathtaking. You start in the 1700s just trying to find the roots of a polynomial equation, and you end up charting the quantum stability of multidimensional membranes inside an infinite categorical skyscraper.
It serves as the ultimate vindication of pure mathematics, the human pursuit of abstract structure, even when it is aggressively divorced from physical reality by figures like Greth and Dieck, inevitably loops back around to unlock the deepest fundamental laws of the physical universe.
What a monumental journey. Let's summarize the ground we've covered today. We started in the classical realm, tracking how the greatest common divisor collapses affine varieties in one dimension,
Right.
and how the Jacobian matrix acts as a gradient criterion to hunt down singularities and self-intersections.
We examined the rigid dimensional chiseling of Krull's principal ideal theorem before watching Grothendieck dismantle the coordinate space. We entered the rising sea, embracing nilpotent elements, arbitrary rings, and the gluing of affine patches.
We've forced our brains to visualize the invisible, the omnipresent generic point, and the dynamic, infinitesimal fuzz of non-radical ideals acting like live photos of geometric collisions, stitched together by the affine communication lemma.
We analyzed the punishing pedagogical reality of Hartshorne's blow-up exercises and how flipped classrooms at ETH Zurich foster a community-driven survival ecosystem.
And we followed that brutal climb to the summit where we uncovered exactly how the geometry forces 27 straight lines to live on a smooth cubic surface, and how the infinite floors of triangulated categories provide the exact stability manifolds required to map the phase transitions of D-branes in string theory.
The architecture of algebraic geometry is unparalleled in its capacity to unify the absolute extremes of pure algebra and quantum physics.
So the next time you see a simple polynomial equation scrawled on a whiteboard, or look at the parabolic curve of a suspension bridge, remember that you're looking at the absolute ground floor of an infinite skyscraper of meaning.
There is always a deeper structure, waiting for the water level to rise.
Which leaves you with one final, lingering thought to ponder on your own. If algebraic geometry allows us to accurately calculate fundamental physical realities, like the phase transitions of D-branes, using tools like infinitesimal fuzz and generic points that exist mathematically everywhere and nowhere, does that imply that our physical universe at its very quantum core is actually an abstract algebraic structure rather than a spatial one? Are we living in the geometry, or are we just living in the algebra? Until next time, thanks for taking the deep dive.